Hi, Assalamualaikum to the panel. My name is Mohamad Rozaidi Bin Marzuki. I am a student in Discipline of Systems School of Electrical Engineering, College of Engineering from UITM. I would like to present to you about my final year project. My final year project title is Steam Temperature Monitoring for Pilot Scale Distillation Column, Linear and Nonlinear Modeling Comparison and PID Control. First, we go to the introduction for this project. Distillation column is commonly used in chemical and petroleum industry. Distillation process works on linear and nonlinear models. Many modeling methods was applied using system identification for the model estimation followed by control tuning process for performance analysis. Many research has been done show that distillation column best work on nonlinear model because it gives better performance and greater presentation compared to the linear modeling. The choice of input data are procedure random binary sequence (PRBS) and multi-level procedure random sequence (MPRS). The performance of the PID control is determined by the proportional, derivative and integral tuning parameters, which are adjusted to match the transient performance requirement. This slide shows the problem statement for this project. In comparison to linear modeling, it has been discovered over the age that the nonlinear model produces better performance and presentation. Unfortunately, using a nonlinear system modeling linear method has significant drawbacks related to the validity of the input set. Furthermore, distillation column control systems have frequently encountered issues or constraints such as difficulty regulating the process and poor control performance. Therefore, this study to investigate the performance comparison between linear and nonlinear modeling using system identification in MATLAB to identify the comparison between the nonlinear and nonlinear modeling. At the same time, using MATLAB for PID control on Ziegler-Nichols, Cohen-Kuhn, Chun-Ron-Redwich, and Takahashi. The objectives for this project are to assess the linear and nonlinear modeling for distillation column, to design PID control using Ziegler-Nichols, Cohen-Kuhn, Chun-Ron-Redwich, and Takahashi, and final to investigate control performance comparison between linear and nonlinear modeling. It is part for methodology. The figure 1 shows the flowchart for this project. The flowchart starts from start to the linear and nonlinear modeling using PRBS and MPRS. After that, we go the model structure selection. Then we go model validation. After that, we decide model accepted or not. So if no, we go back to the model structure selection. And if yes, we go to the transfer function estimation. After the transfer function estimation, we will decide estimation accepted yes or no. If no, we will do again transfer function estimation. If yes, we will do PID control and performance analysis and then end. The open loop test in MATLAB software simulate the input data. For each input, the best fit of the input data is obtained. Simulate the transfer function to get the continuous time equation. Calculate the number Kp, Ti and Td from the open loop result and simulate the block diagram. As a consequence, show the graph of 4 types of tuning that were employed. The RTS and percentage overshoot are used to measure loop efficiency. For experimental setup, a steam distillation power plant (SDPP) with 240 volt 1.5 kW and 50 Hz power was used with a specific sampling time for the emission heating features. The MATLAB software for plant integration and data collection is used for modeling purposes. Figure 2 is a pilot plant that displays the critical oil extraction method. This is process linear modeling estimation were applied. From the input domain, the linear modeling is estimated based on first order plus dead time (FOPDT). After that, the number of holes adjusted several times in the system identification app to obtain the linear modeling estimation. The fitness, final prediction error, and mean square error result will be calculated. Final, use the best fit for the linear model to calculate the PID control. This is part for nonlinear modeling estimation process. From the input domain, the nonlinear modeling is estimated based on a nonlinear autoregressive with exogenous input, or NARS. The number of poles adjusted several times in the system identification app to obtain the linear modeling estimation. The fitness, final prediction error, and mean square error result will be calculated. Use the best fit for the linear model to calculate the PID control. This slide shows the process transfer function estimation. First, from the input time domain, the transfer function is estimated. Then, the number of poles and zeros adjusted several times in the system identification app to obtain the transfer function. Then, the fitness percentage result will be calculated too, but the simulated transfer function graphs must be in the right from the investigate the fitness percentage. Finally, a continuous transfer function equation will be obtained to simulate the model in the block diagram state. This part for PID tuning rule. The controller parameter that tune the process in each mode such as proportional, integral, and derivative when there is a gain that has to be tuned are known as PID tuning rule. It is critical to have suitable methodology for tuning control testing in order to have a high-quality control system. This investigation focuses on well-known tuning such as ZNCC, CHR, and Takahashi. The formula for tuning procedure employed in this investigation is presented in the Table 1. The Table 1 shows ZNCC, CHR, and Takahashi formula for PID controller tuning rule. It is part 4 result and discussion. First, linear model estimation. From the Table 2, it clearly shows that MPRS was more accurate compared to the PRBS. This is because the percent fitness for MPRS was higher than PRBS, which was close to the 90%. However, MPRS at pole 3 was less accurate than PRBS since the fitness was lower. MPRS pole 3 error was also higher than PRBS error. The error and loss function lower is better. Table 2 shows the comparison linear model for PRBS and MPRS input. This slide shows the result of nonlinear model estimation. The Table 3 demonstrates the comparison nonlinear modeling in PRBS and MPRS. PRBS recorded higher fitness percent compared to MPRS. The error and loss function for PRBS was lower than MPRS. So, it good for data analysis. PRBS was more accurate in nonlinear modeling compared to MPRS based on result. The Table 3 shows the comparison nonlinear model for PRBS and MPRS input. Figure 3 shows the graph of linear and nonlinear in PRBS input. In comparison to the linear model, the graphs clearly show that the nonlinear model stimulates the data more accurately. From the graph's nonlinear response, it shows steady constant same as input line. Therefore, the linear model line took more time to steady constant. Figure 3 shows the linear and nonlinear modeling using PRBS input. Figure 4 shows the graph linear and nonlinear modeling for MPRS input. The linear fitness percent was higher than the nonlinear fitness percent. Nonlinear model, on the other hand, have a lower MSE and FPE value than the linear model based on the Table 2 and Table 3 that conclude the nonlinear was more accurate than linear model. Figure 4 shows the linear and nonlinear modeling using MPRS input. This is part for transfer function estimation. Figure 5 illustrates the outcome transfer function estimation for PRBS and MPRS. Figure 5 shows that MPRS have a greater fitness level than PRBS. MPRS have a value fitness of 88.76% while PRBS have a value fitness of 81.26%. When compared to PRBS and PRS exhibited the lowest FPE and MSE value. The FPE and MSE value for MPRS were 5.44 and 5.43 respectively, where the FPE and MSE value for PRBS were 15.62 and 15.61. Figure 5 shows linear and nonlinear modeling using transfer function estimation. Table 4 shows control performance for different tuning methods based on PRBS input. There are two models, linear and nonlinear, and for PID tuning method, there are ZN, CC, CHR, and Takahashi. Below the table, there are two figures. The figure 6 shows the linear model comparison PID control using PRBS input, and the figure 7 shows the nonlinear model comparison control using PRBS input. This is part for explanation based on figure 6 and table 6 and figure 7. The part is control performance for the different tuning method based on PIBS input. For linear PIBS in figure 6 and in table 6, the value of TR and TS in CHR PID tuning produce faster response compared to CC, ZN, and Takahashi. Then the overshoot for CHR presented lower value than ZN, CC, and Takahashi. TP for CHR was higher than other PID. For nonlinear PIBS comparison PID in figure 7 and table 6, in comparison to CC, ZN, and Takahashi, the value of TR and TS in Takahashi PID tuning demonstrate faster reaction. Then ZN produced a higher overshoot than CHR, CC, and Takahashi. However, TP for CHR was higher than other PID. Table 5 shows control performance for different tuning methods based on MPRS input. There are two models, linear and nonlinear model, and there are four PID tuning methods, ZN, CC, CHR, and Takahashi. Below the table, there are two figures. Figure 8 shows linear model comparison PID control using MPRS input, and Figure 9 shows the nonlinear model comparison PID control using MPRS input. This is part for explanation for table 7 and figure 8, figure 9. This part for control performance for different tuning method based on MPRS input. For linear MPRS input, the comparison of PID control performance based on figure 8 and table 7, when compared to other PID, CHR has faster time rise, settling time, percent overshoot, and peak time. For nonlinear MPRS input, figure 9 and table 7 show a comparison of PID control performance for nonlinear MPRS input. CHR presented higher time rise, settling time, and peak time when compared to other PID. However, overshoot for CHR was the lowest than ZN, CC, and Takahashi. This part for conclusion. The conclusion is MPRS was the best for pertute the linear model and more accurate in analysis. PRBS was more accurate in nonlinear modeling compared to MPRS based on result. The performance of linear and nonlinear model PID control was investigated in this research using multiple tuning method. In terms of a linear PIBS, it can be determined that CHR has the best transient response performance when compared to other PID. The Takahashi in comparison to other PID.
has the best performance for nonlinear PIVS. Finally, when it comes to linear and nonlinear impedance input, they shall outperform other PID in terms of transient responsiveness.
Thank you.